So thanks for, after this framing keynote, Barry, thank you for giving me the opportunity to talk about some ideas we've been working up in modeling for collective constraint optimization problems, which is joint work with Guido Tack from Monash and Alexander Knapp and Wolfgang Reif from the University of Augsburg. And let me dive right in. What do we really mean by collective constraint optimization, and why do we think it's a modeling issue in the sense of constraint modeling languages such as Minisync? So assume we are a company that deals with itinerary selection. So we invite travelers to spend a week or two at our place, and we want them to move around here, the virtual neighborhood of Louvain-la-Neuve now currently, and we have to schedule some bus tours that are restricted resources. We can't have everyone do stuff individually. We have to form groups and work up itineraries. So we'll have these travelers that need to be distributed to resources such as the 3 buses we currently have available. And we want to see some of the beautiful sites of Belgium, such as Waterloo or Charleroi or Louvain-la-Neuve. And we might come up with some possible itineraries. So here are 2 sample solutions, the blue and the orange tour that we can offer our travelers. And those might be the ones subject to feasibility, economical constraints, labor availability, etc. And among those feasible ones, we now have to deal with preferences, such as person 16 stating that they want to drive at most 3 hours between 2 sites, or person 5 wanting to definitely see Louvain-la-Neuve and also really bonded with person 1, so they have to be on the same tour. Such a case makes it pretty, so we face constraints, natural constraints. It's collective in the sense of that there are 16 people involved here, and one might think, okay, this seems like a social choice or voting problem. We have to find an agreement between all those agents. We have to align their preferences, but I'll argue that this is not only a matter of voting, and this is what makes it interesting to CP. Naturally, in such a problem, we'll have classical numeric objectives, such as the revenue we get from visiting all those sites or the bookings that we'll expect in the future, which of course might be related to the traveler satisfaction we can guarantee right now or try to guarantee. This is where the trustworthiness aspect will be coming in. We'll have fuel costs, labor costs, or equipment costs that we still want to minimize in order to be economically profitable. In a sense, we have also balancing and fairness, as well as some kinds of biases, unlike those mentioned by Barry. So for instance, the workload among guides has to be spread evenly. Even if one guide has a very famous site that nearly everyone wants to visit, and another person has maybe more of a hidden treasure style of site, so still we need to distribute the workload fairly. That's on the guide side. For travelers, we might want to avoid offering itineraries that only involve physical activities if we think of handicapped people being in our travelers group. And bias in this sense now would mean that we do not really get something along the lines of a dominator, be it by accident or on purpose. So we do not want to have any traveler to be too influential in the group decisions. And I would expect anyone being part of such a travel group to think that this kind of dictator freeness is very interesting. And finally, after all those objectives, we have to deal with these subjective preferences, opinions, and wishes. So I'd like to see the sunrise in Charleroi in the morning, or another person wants more breaks, whereas another one wants to see more sites on a given day. There is no clear way to break this down into one numeric function, even a number of numeric functions as in multi-objective optimization, that makes this really transparent how we aggregate all of these preferences and what will be the outcome. In addition to this little toy example that I've talked now, here are some motivating applications where I believe that AI systems can play a role and benefit from a modeling framework for these kinds of problems. The first one would be all kinds of shared mobility concepts where we do not only have things like car or bike sharing, but really ride sharing and on-demand buses, where we'll have to make agreements with different groups of people that where we have to find consensus in a sense. Manufacturing as a service is a paradigm in the production industry where we as a small business especially, we do not want to have all our machines ourselves, but we rather take turns in a shared facility, and depending on our business going right now, we need to arbitrage between different producers to make sure that everyone gets access to the machines. And finally, smart grids, in particular demand response systems that use electric vehicles or small power plants to adapt their consumption and production to use up renewable sources, are another instance of a constraint problem that involves a number of agents. So some of you in the audience in general might think, well, what's new? Social choice and social decision making has been on the radar of constraint programming or the multi-agent systems community for a while. What's really new that we are proposing right now? So let me introduce some of the related work in this area, in particular in terms of soft constraints and social choice. The groups around Francesca Rossi and Kirsten Brent-Venable have produced remarkable results in sequential voting, where we essentially take a constraint problem as visualized by this constraint graph, and we fix an ordering over the decision variables, and we'll just have each agent vote over the assignment to that variable sequentially. So we might start with what value should X take? Okay, we decide it's 2. Then given X is 2, we decide, well, what's the value for Y? We'll use any voting mechanism. Think of majority. So all agents that want Y to be 1 raise their hands. And now it could be that 1 wins, and eventually, given X is 2, Y is 1, what's the value? What's the best value for Z? That's the sequential voting procedure, which has desirable mathematical properties, essentially lifting some nice qualities about a single decision to a combinatorial one, and has a theory of sequential voting to build on. Unfortunately, it can be kind of myopic in the sense that there are no backtracks and there are no choices cannot be undone. So the agents tend to be overly optimistic, especially here when they cast their vote for X. They might anticipate getting the best value for Z. And of course, this can change throughout such a sequential voting round. In addition, it's a new solving algorithm. It doesn't really make use of any propagation of any search strategies that are available in existing solvers. And that's our angle. We want to leverage MiniSync and the compatible solvers to vote over solutions now instead of domain items in this isolated fashion. On another wing, the distributed constraint optimization community has been dealing with, namely, multi-agent constraint problems. But the focus has been on how can we distribute a constraint problem to a number of agents that are responsible for the involved decision variables and constraints in such a manner that the solving algorithms can be performed in a distributed or asynchronous execution. So there has been much work on really getting all the well-known constraint algorithms to the distributed setting. And some extensions towards social choice have been done, but they are really just a few works. And often the modeling assumption in DCOPS is that we have some additive cost function. So we can express the overall goal as a commensurable or transferable utility. And it really makes the distribution of computational nodes tied together to the solving algorithm, which we argue is not necessarily the case. And again, we want to concentrate on the central question: what should we even optimize for? What's a fair or desirable or nice aggregation strategy? And this is irrespective of the underlying computational topology. So how can we try and do this with mini-Brass or mini-Zinc? And to give you a sense of what we anticipate, here is an example of what we would like to be able to express using a modeling language. For example, we might define for a given problem minimal fairness or balance constraints, such as the guides should be used equally. Under these constraints, subject to these constraints, we want to maybe minimize a monetary objective in a classical sense. So what's the cheapest set of itineraries that we can get to obtain the lower bound for our further calculations? We then want to add some relative slack to the cost bound. So maybe 10% more than the absolute minimum is okay. And now comes an interesting part. Now we want to vote over the feasible set of solutions that's given to subject to the fairness constraints and subject to the cost bounds that we just discovered. And now we want to calculate things such as the Copeland set, a Condorcet winner within the boundaries that we just got. I'll talk about how this could work in mini-Zinc in a minute. And finally, when we have some choice set C of socially acceptable candidate solutions, we again optimize for with our monetary overall cost objective. To make the voting part on the modeling level a bit more concrete, I'll just briefly mention Condorcet voting, which is a family actually of ranking mechanisms in social choice theory based on the notion of a pairwise majority. So assume we just have those 4 options available. The solutions to a combinatorial problem are naturally larger, but here let's do this for the sake of the argument. And we'll form kinds of duals such as, dear population, do you like D better than A? And we'll find out only Dave likes D better than A. And when we ask the converse question, who prefers A to D? We'll see that this is a committee of 3 agents involved here, 3 people involved here. They prefer A to D, and so A would be the winner. And after winning against D, A might have the same kind of dual against B, against C. And in this procedure, we can find a winner if we're lucky. So we want to use this principle now not to vote over a fixed finite set of options, but rather over solutions to a constraint problem. As a little caveat, there might be cycles, but I'll come to that a little bit later. Now, how can we integrate these social choice functions such as Condorcet voting into a CP solver? And this is where it gets interesting for our community, because this can be formulated on the modeling solver level quite easily. Imagine we reach this solution in our search tree. What does that really mean? We now have a candidate solution such as D. And instead of really now comparing it simply to another solution, we might leave this other solution anonymous, but constrain our problem such that it has to produce a solution that is preferred by a majority of agents. We post an additional get better constraint in terms of Condorcet. And this simply counts, well, the next solution you'll find has to be liked more by a majority of agents. And a prototype, this is formulated in terms of mini search and was prototypically presented last year at last year's CP. What we think is that this is very, very easy to do in constraint solvers and modeling languages in general, which might give us an edge over other optimization frameworks such as MIP or other mathematical formalisms. So there are still several implications of social choice for CP solving. enumerating all the solutions that we might need to formulate concepts such as border, Copeland, or Kameny is in general prohibitive, and we cannot expect to really have all the solutions rolled out in advance. Still, we're dealing with hard problems, and we can only hope for an approximation or a statistically significant sample of our solution space. Local search strategies, such as large neighborhood search, may lose direction due to Arrow's theorem. So this could mean that when we are presented with a whole set of options, we would now like B better than C, for instance. But if we only see a subset, our choice might flip, and now we like C better than B. That's one of the famous implications of Arrow's theorem. And it's basically exactly the situation we face in local search strategies. So we should be aware of that. And Condorcet style social choice might suffer from cycles. So it can be that there is no clear winner that dominates all of the other solutions, in which case we would rather go for one of the solutions in the so-called Smith set, so a top cycle that at least dominates every solution out of it, but among the cycle, we cannot really find a winner. So to realize all of this, what's needed from MiniSync? First of all, we would need a library of constraints that can be used to express fairness and balance conditions. This should be a rather straightforward part, but we'll have to look into the literature, what's already there. We would need propagators to formulate all of these fairness conditions, but maybe some of them amount to cardinality. We definitely need a meta search framework that allows us to implement iterative solving algorithms that remove and add constraints in every iteration to really be able to express different kinds of strategies, to eventually implement different kinds of social choice functions that need more state than just going from one Condorcet dual to the next one, to implement a variety of social choice functions. And we thought about what's the contribution to this trustworthy AI workshop. We really believe it's important to define what can be transparent and faithful optimization criteria. So the usual situations when we go to people working with a model is, well, of course, this solution is better. It has objective value 1447, and this is actually more than 1445. But we might want to get more involved explanations. And so I'm really excited for the next two talks because I really face this problem quite a lot. And similarly now in collective problems. And what rules for preference aggregation will actually be used? We know this from electoral systems. People will find all kinds of weird cases and try to manipulate the system in their advance. And even if there's no malevolence, we want to be able to explain and derive how our social aggregation mechanism worked. So to conclude, we believe that collective constraint optimization problems are multifaceted, and a lot has happened in the community since the first ideas to collective constraint solving. And we need to take account of those stronger solvers that we have today. We need to blend in voting algorithms with classical objectives and constraints. There are some social choice functions which we already can implement on the modeling level with any existing solver. And an important question remains, how can we really scale this up to large combinatorial problems? Can we get lucky with local search, or will Arrow be our enemy that makes all of these approaches useless? So I'm, yeah, exactly. So I'm looking forward to discussions on the white paper in the afternoon and open for any questions or suggestions.